Let's talk more about line search, a lot more about line search. In our previous module, we said we were doing line search methods, and we said, okay, I'm going to go along the gradient, but we didn't really search along the gradient. We just said, I'm going to go half the distance that the gradient tells me to, or 0.01 the distance or something. And we didn't actually search, but then we had to try different learning rates and see which one was the best. Now we'll do the opposite. For any one step, we're going to make a careful or somewhat careful search along the gradient to find a minimum in this direction, which takes longer on that step. But then we won't have to try different learning rates for the entire optimization, so it's a bit of a trade-off. Also, on the problems we've worked on so far, the objective function was like the sum of squared residuals or mean square residual or mean or sum of log likelihoods or something in logistic regression or cross entropy. And we could say, well, if the data set is too huge, I'm just going to take a small bunch of terms and do the stochastic gradient thing. But now we'll mostly be imagining that I'm going to evaluate the entire objective function, either because you can't separate it into different terms, or maybe because we just don't need to, it's fast enough. So some examples of objective functions that are like that, this one here is basically a linear program with an objective function 7x plus 11y, and we're minimizing, but we have constraints, and here I put the constraints in the objective function by penalizing them, or actually putting up a barrier, saying if you get too close to the constraint, your objective function goes up. So it's kind of like putting an electric fence around on the constraints and saying don't get too close. And you might say taking a linear program and writing it in nonlinear terms sounds like a bad idea, but it's actually a really good idea. And we'll talk about that more later in the course. Another place that we might have an objective function that you can't break down into separate parts is one we've already talked about a little bit with the blood sugar and insulin problem. Let's remind ourselves of that. So here we were trying to adjust how aggressively we're adding insulin in response to blood sugar and see how close we are to our target. So instead of a 3 here, I might have like a 2.4, for example. So these are my decision variables. That's my objective function. And I've got what looks like a bunch of data here, but each row depends on the row before it. So I can't just take a random sampling of rows. So those are two big use cases for what we're talking about now. Let's go take a look at some graphs in Desmos to kind of orient ourselves. Here's a two-dimensional problem, and here's our objective function. It's the same thing I just showed in the other sheet. So it's a linear programming objective function plus some penalty terms, or barrier terms, I should call them. So imagine right now we're here, and we've determined that the gradient is pointing in this, the gradient itself is pointing in this direction. We're minimizing, so we want to go this way. And we know the current objective function value is 29. So I could say, well, let me try going 1 times the gradient. Oh, that's going backwards. Let's try -1 times the gradient. And that gets me down here, which is actually infeasible. So we can back off a bit. We can say, how about -0.1 times the gradient? And I get a slightly lower objective function value. And I could say, well, let me try going a little farther. How about -0.2? And that's even lower. And then -0.3, that's even lower. -0.4, ooh, that went up a lot. So that's kind of what we're talking about here, trying different size steps along the negative gradient, seeing what the objective function value is, maybe going too far, backing off a bit. What we're not seeing in this graph, because in some sense we can't see it when we're actually optimizing, is the contours of the objective function. But let's show those just so we can think about kind of what's going on here. So this is the contour we're on. Our gradient or negative gradient is perpendicular to the contour, and we're trying to go downhill and not go too far uphill on the other side here. But remember, we can't see the contours when we're actually doing the optimization. Another way to think of this is by doing a cross section along this search direction, and I have that programmed here. So now the x-axis is how far along the search direction you're going, and actually I have that shown here. We're saying take where I am right now and add some scalar multiplier times my search direction. if I increase my x value here, that isn't x in my original problem, that's alpha. It's essentially my learning rate, but it's specific to this one, and I'm trying different ones even on this one step. So right now, I'm calling x1 alpha here. So I could go, how about 1? And where does that end up? It's not even on the screen here. I could try 0.1, and I end up there. How about 0.2? I end up there. 0.3, I end up there. 0.4, not visible on the screen. So maybe it's shot way up, or maybe it's infeasible or something. So I'm basically trying to try different values here and get hopefully something close to a minimum. That will finish this step, and then I'll take the gradient and take another step. Again, let me show something that we wouldn't actually be able to see when we're doing the optimization, but we're kind of trying to find out how this function behaves by sampling a few points. And here apparently it shoots to infinity by the time you get to 0.4, so let's not do that. So overall, our goals now are to find a reasonably good minimum along this search direction. We don't actually have to find the absolute best minimum, but just getting in the neighborhood is probably good. We don't want to evaluate the objective function a lot. And while derivatives can help speed our search, if they're hard to compute, maybe it's not worth the extra trouble. So again, we just have this common trade-off of, do I want to do a really good job optimizing along this direction and take a long time and then probably take fewer steps toward the overall minimum? Or do I want to do a not so thorough job along this search direction but save some time and then maybe take more steps? Do I want to use something that might be expensive to compute or not? So those are the trade-offs we're keeping in mind.